In this section, we will discuss pilot tracking in OFDM systems. We will give some examples from 802.11a, some simulation results. We will talk about how to estimate the channel from the pilots, and we will also discuss fast fading channels as will be encountered in mobile wireless access networks. I will also go over the pilot allocation scheme used in 802.16-2004 in the OFDMA Metropolitan Wide Area Network. Here we show two schemes that can be used for allocation of pilots in an OFDM system. The top part makes sense, in which case every other OFDM symbol, for example every fourth OFDM symbol, we allocate all carriers to pilots, and in this way for that particular symbol time we can use all the pilots in order to estimate the channel frequency response at every carrier location. And then every, for example, fourth symbol, we send the pilots again and estimate the channel. So if the channel is time varying, in this way we can track the time varying channel. Another way is to use a comb type pilot subcarrier arrangement, which we show over here. In this case, every OFDM symbol contains carriers at fixed locations, and in this way for every OFDM symbol we can estimate the channel. The difference with the top is one of the differences with the top. The block type pilot subcarrier arrangement is that for every OFDM symbol we only have in this case 4 pilots, whereas in the case for the block type pilot subcarrier arrangement all the carriers in an OFDM symbol are pilots. However, one advantage with the comb type pilot is that if the channel changes rapidly on even a per OFDM symbol basis, then using the comb type arrangement we can actually track a fast fading channel better than in the case of the block type. And people have done research and published in the literature, and this happens to be the case, that the comb type pilot subcarrier arrangement actually performs much better than the block type in fast fading channels. 802.11a, for example, uses a comb type pilot subcarrier arrangement, as does 802.16-2004 OFDM, the 256.8 OFDM, and we'll show that in a minute. By the way, we will be dealing with the comb type pilot subcarrier arrangement throughout. So in this block diagram, when we receive a OFDM symbol, here we're showing it at the receiver after the fast Fourier transform, where we have converted the time domain OFDM symbol into the frequency domain. We have this block here which extracts the pilots from the OFDM symbol. In this case, for example, we have 4 pilots. Then we have a block which estimates the pilots from the received signal, y sub p, and we'll show how that's done. And this is based on knowledge of the known pilots. So we feed the knowledge of the known pilots into this block, and we actually have the received pilots, and therefore we can estimate what the channel response is at each particular pilot location. Now there are many ways to do this pilot signal estimation. Some schemes take into consideration some extra knowledge, and in particular the noise in the channel, and achieve a better estimation. If you ignore the noise in the channel, then you can still estimate the channel response at each pilot location. However, when you have noise, these schemes, their performance deteriorates. So we'll get into that, and there's a lot of the literature deals with the actual estimation of the pilot signal from the received signal, using the known pilots and the fact that you've received the actual pilots through the channel plus noise. Once you've estimated the channel response at the pilot locations, then we perform a channel interpolation in order to get the estimated channel response for every carrier, because we have to obviously equalize each carrier of the OFDM symbol. Here we have the actual channel response, frequency response, as a function of frequency. We're showing the magnitude. And we have the actual carriers. What we're trying to do is estimate what the channel frequency response is at these carrier locations, so especially at the data carrier locations. Now what we have are the actual estimate of the channel at the pilot locations. In this case we're showing 3 pilots. So once we've estimated the channel response for each pilot, then we have to go through a interpolation scheme in order to find out what the channel frequency response is for each data carrier, so that we can actually equalize the data carrier with knowledge of the channel frequency response at that carrier. In this diagram, what we're showing is actually piecewise linear approximation for the interpolation. So we do a piecewise linear approximation between these 2 pilots, and for each data carrier then we estimate the channel frequency response at this carrier using this piecewise linear approximation. We do the same thing between these 2 pilots here. And we'll show some performance curves for this scheme. There's more advanced schemes than this, and we'll show the difference in performance later on. But this gives you an idea, going back to the previous block diagram, that if we have samples of the frequency response of the channel at the pilot locations, then we can perform a channel interpolation and then find out an approximation to the channel frequency response at each data carrier location, and then we can use that to equalize the channel on a per carrier basis. Now there's an interesting lemma and a theorem that was presented by a paper by Neghi and Cioffi back in 1998. And before we present that lemma and the theorem, let's go over some equations here that are straightforward. In the following, L is the maximum length of the channel in samples. So if the channel impulse response had L samples, then that's what we mean by L. So L is the maximum length of the channel impulse response. And we'll show examples of that. For example, if you look at a power delay profile and then find out where the impulse responses fall off, at a certain point they're negligible, and then you can find L, the maximum length of the channel impulse response. X of k is actually the constellation point that was transmitted through the OFDM modulator. So the OFDM modulator basically does an inverse FFT and takes the constellation points that have been grouped together along with the guard intervals and the pilots and the null at DC, for example, and you take the inverse FFT and you come up with a time domain. Then at the receiver you do a forward FFT and recover the original constellation points. So X of k is the original constellation point at a particular carrier, in this case carrier k. We have n carriers, so this is shown as X of k, where at k goes from 0 through n minus 1, where we have again n carriers. As the carrier goes through the multipath fading channel, then we have the frequency response at that carrier frequency of the channel, which is h of k. So we get h of k times x of k plus noise term associated with the noise in the channel. The index m is related to the time varying impulse response. So at a particular time m, we have a particular impulse response for the channel, and at that particular channel then this is the actual received signal at the output of the FFT and the OFDM demodular y sub k, comma m. So we can actually define a matrix H sub m, which is basically the impulse response of the channel, which has L samples H0 through HL minus 1, and m is the actual mth impulse response. Now if we take y sub k sub m and divide it by xk sub m, then we recover hk sub m, shown over here. But what happens is that since we have a noise term here, our channel estimate is contaminated by the noise, and sk sub m is related to vk sub m through this expression here, where we're just basically expressing xk comma m in terms of its magnitude and phase. Here we're showing the magnitude and incorporating the phase into the noise term. So the mathematics here is basically simple. What we're saying is that we have a carrier that goes through a channel with channel frequency response at that carrier h of k, and we add noise through the channel and we receive the signal y of k, which is the received carrier at the OFDM receiver after the FFT. Then if we know what x of k is, we can actually divide y of k by x of k, and we actually get r of k, which is an estimate of the channel frequency response at carrier k plus a term associated with the noise and the carrier. And usually pilots have a magnitude equal to 1, so the magnitude x of k is usually equal to 1 in most cases. So that's basically what this is saying, and the index m is due to the fact that we have a time-varying channel and the impulse response of the channel changes over time. Now, the paper by Negi and Cioffi has an interesting lemma, which is as follows. The lemma basically states that in the absence of noise, any L of the n available tones can be used for training to recover the channel H exactly. So if H is the impulse response of the channel, and the impulse response of the channel has n samples, then if we allocate of the available n tones that are transmitted, if we use L of them as pilots, then we can completely recover the channel impulse response exactly. Now we won't go through the derivation here, but it basically works as follows. The set of pilots tones are located at these indexes, for example K1, K2, K through L, and then we have the frequency response of the channel at these pilot locations K1 through K sub L, shown over here. And basically we have that mathematically this set of sample points of the frequency response at the pilot locations is related to the channel impulse response through this matrix shown over here. And without diving into too much detail, this matrix is the similar matrix that you see used for a forward FFT, where we relate the time domain to the frequency domain in the discrete Fourier transform, and the W's are related to the routes along the unit circle. And what we want to say is that this matrix here is a non-singular matrix, therefore it's invertible. So if at the receiver I have the estimated response of the channel at the pilot locations, and I have L of them, and I know this matrix here, then I can invert this matrix and actually compute H. For example, if I multiply both sides by the inverse of this matrix, then I get H is equal to the square root of n times the inverse of this matrix times H. And I know H because these are the actual estimates of the channel frequency response at the pilot locations. So this basically says, which is very interesting, that if I have a channel impulse response that has L samples and I use L pilots among the total n number of available tones, and if there is no noise in the channel, then I can estimate the channel impulse response exactly, which is H. Now there's a very interesting theorem also that is also due to Negi and Cioffi here, and this is very important, is that, and I'll just read it off, it says that when the noise is additive white Gaussian noise, then the minimum mean square error estimate of H, the channel impulse response, occurs when the set of L pilot tones is one of the sets I plus n over L, etc. So basically what it's saying is that the optimum choice for the placement of the pilots is that they're equal distance apart, as shown over here. Then that'll get you the best algorithm for estimating the channel impulse response. This is very important. Although this is done with the case of additive white Gaussian noise, things are a little bit different when you're dealing with actual radial fading multipath channels and fast fading, and we'll show that later on. But in general, if you're in particular dealing with a fixed wireless access network, then this theorem states that the best choice is to actually place the pilots at equal distances apart. And that's precisely what is done in 802.11a and 802.16-2004, or 802.16a, for example, for the 256-point FFT. So this is a very interesting theorem. So we haven't done any particular complicated mathematics here. We refer to the paper if you're interested. But what we're basically saying here is that if the channel impulse response has L significant samples, then if you have L pilots within your N tones, then you can precisely exactly estimate the channel impulse response and therefore the channel frequency response if you have zero noise in the channel. The second theorem says that even if you have additive white Gaussian noise, then the best minimum mean square estimate of H occurs when these pilot tones are spaced equal distances apart, as shown over here. Let's take a look at this diagram. At the top, we're showing the channel frequency response for the case where the RMS delay spread is 50 nanoseconds, and this is for a channel which is 20 megahertz, say at 5 gigahertz, for example, for 802.11a. So the bandwidth is 20 megahertz, and we're showing the fading channel for a RMS delay spread of 50 nanoseconds. The power delay profile is shown over here. We see the exponential decay, and you can see that for the case of 15 nanosecond RMS delay spread, the impulse response dies out after a certain number of samples, and this is the number that you associate with L. So for example, in this case, if we use 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, or 10 pilots, then we can estimate the channel perfectly with 10 pilots. That's what the lemma in the previous slide showed. So let's take a look at the pilot arrangement in 802.11a. As we've indicated, in 802.11a you have 64 carriers. Of these carriers, some of them are the guard interval or null carriers on the, in this case, on the left side, and on the right side, and you have a null at DC. You have 48 data carriers, and you have 4 pilot carriers with a total of 52. So these pilots are used in 802.11a implementations in order to not only estimate the channel after the initial acquisition and channel estimation equalization, but if the channel does change due to motion, for example, you have Doppler shift, you can actually track the channel changes using the pilots. Now the pilots are also used for tracking residual carrier offset estimation error and also timing drift. We'll get into that. We also indicate that the spacing between the carriers in 802.11a is 312.5 kilohertz as shown over here. For the case of IEEE 802.16a, for the OFDM Metropolitan Wide Area Network, where we use a 256-point FFT, again we have the nulls on the left and the right. We have a null at DC, and we have 8 pilots in this case. So for OFDM and WiMAX, we have 8 pilots. And notice that the pilots are spaced apart at equal distances, which is the best spacing for a minimum mean square error estimator for the channel impulse response, as we indicated, especially for fixed wireless networks. Now here we're showing the constellation of the pilots for 802.11a. This is an actual simulation of a 802.11a transmitter and receiver with additive white Gaussian noise. The signal noise ratio is equal to 24 dB, and we're actually showing the results for 4,000 bytes, so this is over a very long packet. And you can see that due to the, even though we are using both coarse and fine carrier frequency offset estimation, due to the large noise there is going to be a residual carrier offset, and if we don't do pilot tracking, then the pilots actually drift, as you can see here. They're actually rotated. As you can see, this will actually cause intercarrier interference and destroy the orthogonality of the OFDM carriers, and obviously the system would fail after a while. However, if we turn on pilot tracking, then we're able to actually get the constellation show over here and correct for the drift due to the carrier frequency offset estimation. So it is very important for the pilot tracking algorithm to be able to actually track the error due to rotation caused by residual carrier frequency offset estimation. Now for the case of 802.11a, we have 4 pilots, and each pilot is going to be rotated compared to its original position, and we can actually calculate the amount of rotation, And the amount of rotation is directly related to the amount of the carrier frequency offset. And we have 4 pilots, therefore we can actually average them, and you can actually estimate what the carrier frequency offset, residual carrier frequency offset is, and eliminate it as shown over here. So there are various algorithms for doing this, and we'll leave that up for implementers, but the basic idea is that you can actually, with 4 pilots, estimate what the carrier frequency offset is over time and adjust for it and correct it. Here we show the constellation for 54 megabits per second with no pilot tracking, with pilot tracking turned off. And in this case we had 100 kilohertz carrier frequency offset, and although we are doing coarse and fine carrier frequency offset estimation and correction, there is always a residual when you have noise, and over a long packet this is causing the constellation to rotate. If we turn on pilot tracking, then we're able to actually correct for that, and we get the constellation shown over here, in which case we actually had 0 errors in the packet. So it does a fine job of correcting for residual carrier frequency offset estimation error. Another issue that we have to deal with in tracking pilots and use pilots to actually correct for is timing offset. As we show over here, timing offset is due to the fact that at the transmitter we use these locations to sample the signal. At the receiver we sample at a timing offset compared to the transmitter, and this timing offset creates a problem that we will show, and we have to actually correct for this. Now, if we take a look at the Fourier transform pair shown over here, a delay in time translates to the following in a frequency domain. So we basically get a phase shift due to a time delay in the time domain. So a time delay in the time domain becomes a phase shift in the frequency domain. The phase shift is directly related to the delay in the time domain. So this is a very important relationship. Let's take a look at the situation here. In 802.11a we have 4 pilots. If we have a timing offset of 12.5 nanoseconds between the transmitter and receiver sampling, then this is what we see in the pilots. Basically, we have 4 pilots. The pilots are located at 4 different frequencies, shown over here. So we got pilots at 4 different frequencies. Therefore, if we look at the expression over here, for a given fixed time delay, each pilot would have a phase shift that depends on the frequency of the pilot. That's why we see the different phase shifts corresponding to the different frequencies of the pilots. So if we take a good look at this, we can see that we can actually, since we know what the frequency of the pilot was and the amount of phase shift, we can actually estimate the time delay on a per pilot basis and then average over the 4 pilots to actually get the time shift, and then correct the time shift for all the data carriers. Now that's one way to do it. Again, we're not getting into the implementation, just showing you the concept. Over here, if the time shift is smaller than we see that the phase shift is also smaller. In fact, you probably can't even distinguish very well these 2 pilots, but when the phase shift increases, you can actually see the 2 separate pilots at the separate frequencies. And there's also papers in the literature that point out that sometimes, especially when you're trying to track time varying channels due to fast Rayleigh fading, sometimes you actually have to take into consideration the time shift due to timing offset and correct for that, estimate that and correct for it as you use the pilots in order to interpolate the channel frequency response. So this is an important issue. So let's take a look at this situation. Here we have the actual constellation with timing offset of 12.5 nanoseconds for the case of 802.11a, and we're showing the pilots also, as we indicated before. And what happens is that now, the point we want to make here is the fact that if you have a fixed timing error during the initial channel estimation and correction, the timing offset, since it manifests itself as a phase shift in the frequency domain, can actually be incorporated into the channel frequency response of the channel, so that during acquisition, when you do the initial channel estimation and equalization, you can actually equalize out the effect of the timing offset. So the timing offset is actually corrected during the initial channel estimation and equalization. However, for long packets, there's a drift due to temperature and so forth between the clock at the initial acquisition stage and as you process more and more OFDM symbols. And as that clock drifts, then the pilots are used to track the additional timing error and correct for them, as we pointed out before. Here we show the actual constellation after correction for the timing offset error. Now, pilot tracking is also very important in terms of combating Doppler shift when you have mobile wireless access networks. As we pointed out, when you have a vehicle, for example, moving at very high speed, then the carrier that's received by the access point or base station in particular will exhibit a Doppler power spectral density. There is a spread due to Doppler, which is related to the carrier frequency and the vehicle speed, and this causes deep fades in the envelope of the carrier over time, which is very detrimental to the communication. In other words, the channel is changing rapidly over time. So in this case, the pilots can be used in order to track the changes in the channel and correct for them on a symbol per symbol basis. So in the implementation that we did back in 2002, we have a very powerful pilot tracking algorithm, in which case for a vehicle speed running at 200 meters per second at 5 gigahertz, we're showing the pilots without pilot tracking, and we can see they are changing with time due to vehicle speed. However, if we turn pilot tracking on, we see that the pilots are equalized correctly, and we can track the pilots and then apply the results to all the carriers. So we can see that in the next plot. So here we see the constellation with pilot tracking turned off, and you'll notice that the constellation points, of course, move around due to Doppler shift. If we turn pilot tracking on, then we get the constellation show over here, and we're able to decode the packet correctly. And this is at 200 meters per second at 5 gigahertz using only 4 pilots in 802.11a type of environment, although it wasn't even designed for this high speed. So what we want to do is deal with the cases where we have a fast-fitting channel in OFDM, as we encounter in, for example, 802.16e. In the case of high-speed mobile wireless access networks, what we need to do is every nth OFDM symbol, we're going to obtain an estimate of the channel based on the pilots in the OFDM symbol. And initially we have, during the initial acquisition by processing the preamble, we have an initial estimate of the channel impulse response shown over here. For example, starting with n-1 equal to 0, for the initial case we have the initial channel impulse response estimate based on the processing of the preamble. But over time the channel changes, especially at high vehicle speeds, and on a symbol per symbol basis, for example, using the comb type pilot allocation, then every OFDM symbol has multiple pilots. These multiple pilots are then used in order to estimate the channel and interpolate the channel, and then estimate what the impulse response of the channel is. And we're showing that by this term here, which is h hat of r sub n. So this is the actual estimate of the channel impulse response at the nth OFDM symbol using the pilots in the OFDM symbol. Then we can actually update the estimate of the channel impulse response with the previous estimate and the new estimate using the formula shown over here, where alpha is a forgetting factor. For example, if alpha is equal to 1, then we only use the estimated impulse response during initial acquisition. Alpha is usually going to be very close to 1, so that as we get more information about the changing impulse response of the channel on a per symbol basis, then we can update the actual impulse response estimate of the channel. Now this is a very interesting result from the paper shown over here. The actual placement of the pilots, we indicated before that in the paper by Nagy and Cioffi, we indicated that according to them, with an additive white Gaussian noise channel, the best way to place the pilots is at equal distances apart in a comb type arrangement. And here we show that for example over here we're showing the arrangements of the pilots, and you'll notice that they're all separated by 4 carriers. And this plot here shows the result where we're actually varying the signal to noise ratio, and then we're showing the gain, the signal noise ratio gain, given the fact that we're actually estimating the channel, updating the estimate of the channel impulse response on a per symbol basis using pilot tracking. And as you can see over here, for the case A, where we have equal distance pilots, this is this case over here, the actual SNR gain is shown here. However, if we arrange the pilots according to this arrangement D, where you can see that we have the pilots sort of clustered together, but then offset, for example, we see that in this case, we get the best performance. So for case D, which is shown over here, we get the best performance in terms of signal to noise ratio gain. So this has to do with the fact where we're dealing with a fast fading Rayleigh channel, and in that case, recall that the case where the equal distance pilots was the optimum was the case where we had additive white Gaussian noise. But if you actually have fast Rayleigh fading channels, then you can come up with schemes where you place the pilots in an appropriate way to get much better performance. So I refer you to the paper shown over here. So going back to the block diagram, just in preparation for the next slide, what we're showing is the fact that we receive the signals y sub k. We have certain carriers that were dedicated to known pilots. We feed the known pilots into the pilot signal estimation. We receive the actual response due to the pilot. We know what the pilot is, therefore we can estimate what the channel frequency response was at that pilot location. And then we go through a channel interpolation algorithm and obtain the channel frequency response at each data carrier location. And then we can actually do a per carrier equalization using the zero forcing method as an example. Now we have 2 references that I'm showing over here. One, this quotation is straight out of this paper here, and they reference Zhao's paper down here and this paragraph here. And basically, in a nutshell, what this paragraph is saying is that Zhao had an interesting way to do the interpolation, in which case after they estimate the channel frequency response at the pilot locations, then they use a DFT to transform that into the time domain. They do zero padding, and then they do an inverse DFT to get the interpolated channel frequency response. And in this way, they actually get a much better result. For example, they get anywhere between 1 dB and 3 dB improvement in performance compared to, for example, a piecewise linear type of interpolation. And then basically, folks over here actually show an improvement over this method. So that leads us to the next slides. Now the purpose of this graph here is not only to show that different algorithms for estimating the pilots and doing the interpolation give you different results. Some are much better than others, but some of them come at a cost in terms of complexity. But actually, one of the reasons that I'm showing this graph is to show you the impact of a fading channel on the performance of the OFDM system. So let's take a look at this situation here. We have a system which is using 16 QAM with 1024 point FFT. The number of pilots is 128. The carrier frequency is 1 gigahertz and the bandwidth is 2 megahertz. By the way, this is from the paper over here. And what we're seeing is the fact that, first of all, they have a method which is a minimum mean square error method plus phase compensation, for example, shown over here. This is the result they get, which is one of the best results. And the actual piecewise linear technique that we indicated at the beginning, is the results are shown over here. And Zhao's algorithm that we mentioned is shown over here, which uses the DFT and then zero padding and inverse DFT is shown over here. So this is to indicate that you get much better performance sometimes if you're willing to use more sophisticated algorithms. What we're also showing is the fact that this is the bit error rate for a slow rating fading channel with a vehicle speed of 6 kilometers per hour. And you'll notice that as we increase the signal to noise ratio, the EB over N0, then the bit error rate goes down. And for this particular method, it continues to go down, whereas for these methods, we sort of start to lose it, even though we're increasing the signal noise ratio. So this is significant in terms of the algorithm you use for the fast fading channels. Now keep this curve in mind, and let's go to the case where we have fast Rayleigh fading, in which the vehicle speed is increased to 150 kilometers per hour. So now we have fast Rayleigh fading. And in this case, you see that the bit error rate is very low compared to the previous case, where we can actually achieve a bit error rate of, for example, 1,000th, but over here we can barely get 100th in the case of the fast Rayleigh fading channel. So the fact that the channel changes considerably affects your overall performance, and again we see the improvement due to the more sophisticated algorithms, as you can see over here. So basically, compared to the other one, we see when the vehicle speed increases due to the rapid changes in the channel, even though we're doing a per symbol pilot tracking and channel estimation to track the changes in the channel, we still lose quite a bit of performance because of the high speed of the vehicle. The next topic we want to get into is the method used for pilot allocation in OFDMA, OFDM multiple access, and IEEE 802.16a, for the case which we're using a 2048 FFT, because there are certain issues that are involved with the pilot allocation when we do OFDMA, and that's why we will discuss this in a little bit more detail. This paragraph is straight out of the IEEE 802.16a document, and I'm reproducing it here because they've done a great job in explaining how all this works and why they need to do the pilot allocations the way they do it in OFDMA. And basically this is very important in the fact that in the downlink you only have one set of common pilot carriers that is received by all the subscriber stations, because you can think of it as the base station transmitting to all the subscriber stations, and all the subscriber stations have to use the common pilot carriers transmitted from the base station in order to do their pilot tracking chores, so to speak. But in the uplink, each subscriber station transmits its data burst through subchannels, and therefore every subchannel has to have its own set of pilot carriers. So the pilot carriers that are allocated during the data burst from the subscriber stations back to the base station have to be allocated differently on a per subchannel basis compared to the case where you have common pilot carriers across all the carriers in the case where you're using the downlink. So let's take a look at this. Here we show the data burst for a TDD frame, for example. We have the downlink subframe, the uplink subframe. In the downlink subframe, recall that we send a common preamble to all the subscriber stations, and then you have the actual maps and the data burst, the downlink data burst. Now what we want to point out is that in the downlink subframe from the base station to the subscriber stations, a common set of pilots are used that are common to all these subscriber stations during the downlink subframe. However, during the uplink subframe, each subscriber sends its own data burst back to the base station, and therefore it has to allocate its pilots for its data burst, and the location of these pilots changes on a subscriber per subscriber station. So each subscriber will have a different allocation because it has a different data burst, which is described by its allocation in terms of its subchannel offset, number of subchannels, and time slot offset, and the number of time slots, for example. So this subscriber would have to allocate its own pilots that change depending on its data burst. So that's the issue that we want to deal with, and the fact that, and the other issue that we want to talk about is that the pilot arrangement in 802.16a also differs quite a bit from the pilots that you are typically used to in terms of 802.11a or 256.FFT, OFDM and 802.16a. And we'll show that in a minute. First of all, in the downlink pilots for OFDMA, we have the total number of carriers. The size of the FFT is 2048. We have 142 pilots which vary in location, and we'll show that. This is a big distinction with what you've seen before in terms of the pilot arrangements in, for example, 802.11a or OFDM and 802.16a. Is a sense that in OFDMA, the actual locations of pilot change on a per symbol basis. We'll show that. There are 32 pilots which have a fixed location that don't change. Now it turns out that of the 142 pilots whose location varies, some of them coincide with the location of the fixed pilots, and that number is 8. So the total number of pilots is actually 142 plus 32 minus 8, which is 166. That's the total number of pilots used in the downlink subframe in OFDMA. Recall that the number of data pilots was 1,536, and the total number of used pilots is 1,702, which is equal to this number plus 166. Now this nice diagram shows what's going on. If you refer back to the standard itself, there's a number of equations that actually give you exactly what the index is of the pilot. This picture, also adapted from the standard, shows clearly what's going on. In the case of the downlink subframe used in OFDMA, the pilots are arranged as follows. Here we show the carriers for an OFDM symbol. So for example, here we're sending one OFDM symbol which is made up of 2048 points, but here we're only focusing on the end used points because we're only interested in the data carriers and the pilots, ignoring all the other carriers. For example, the null carriers in the left and right guard intervals and the null at DC. So in this case, end used is equal to 1702 number of carriers. Here we're showing, for example, one OFDM symbol in terms of its carriers. Here's the subsequent OFDM symbol, and then the next OFDM symbol, and so forth as a function of time. Also note these numbers here. L equals 0, 2, 1, 3, and then L equals 0. L is a number that's provided in the standard, which goes from 0, 1, 2, and 3, but not in that order, but in the order shown over here. And based on L, you can actually find out what the location of the variable pilots are. So recall that the number of variable pilots was 142, and they have to be distributed among the end used carriers. So for L equals 0, we're showing where the variable pilots occur, and you see that they're spaced at equal distances, and these locations are determined by L equals 0 in this case. So for the next symbol, usually we're used to the fact, for example, in the comb type arrangement of the pilots, that the pilots were in fixed locations, but now we see that the pilot has actually changed locations. This is the variable pilots that are whose position is changing for the next symbol. As we go to the next symbol, we see that the location of the pilot again changes, and it's dependent on this L equal to 1. In case where L equals 3, we see that the pilot changes again, but again we're talking about equal distances between the pilots. The red pilots are the fixed pilots, so here we're showing the fixed pilots and then the variable pilots in the orange. Now after the fourth symbol and the fifth symbol, the pilots are arranged exactly as in the first OFDM symbol, so the process repeats. So after 4 symbols, we get the same pilot arrangement that we had in the first symbol. So what are the benefits of the fact that we have variable pilots and their location changes is that we get diversity. So if, for example, we had a channel where we had a null or a deep fade, then the pilots actually change locations and we get a diversity gain by having these changing locations, especially when we're dealing with fast rarely fading channels in which the channels can change quite a bit from symbol to symbol. We can still use these pilot locations in order to estimate the channel at the pilot locations and then still perform some kind of interpolation to estimate the channel impulse response and equalize the channel. Now this is for the downlink common pilots. Now notice that these pilots remain the same. The pilot locations remain the same in the sense that for the downlink subframe they all change according to this arrangement on a per symbol basis, but all these pilots are the same in terms of all the subscribers receive the same set of pilots, although they change on a per symbol basis. In the case of the uplink subframe, things are different. So before we get into the uplink subframe and the data burst from the multiple subscriber stations back to the base station, first of all, we'll note that for the uplink subframe, we have 1,696 used carriers. We have 32 subchannels. Each subchannel contains 53 subcarriers. So unlike the downlink frame where we had 48 carriers per subchannel, in the case of the uplink we have 53 subcarriers per subchannel and we have 32 subchannels. Of these 53 subcarriers in a subchannel, 48 of them are data carriers. So we have 5 pilots that are used in each subchannel. So here's the key. Every subscriber station is allocated by the uplink map a region for its data burst, and the region specifies subchannels and OFDM symbols. Now, since each subscriber station has a subchannel associated with it, then it has to pack the pilots into its subchannels when it sends its burst back up to the base station. So the position of these pilots changes on a subscriber by subscriber basis. That's the idea about the variable pilot locations in the uplink data burst. So let's show that. Now here what we're showing is the arrangement of the pilots within a subchannel. So again, this is time and this is the carrier index, and we're looking at one subchannel. So for a particular subchannel we have 5 pilots that we need to allocate. Of these 5 pilots, one pilot is a fixed location pilot that is shown over here. So we have one fixed location pilot. So on a symbol per symbol basis, its position does not change. Then we have 4 other pilots. Now again we have this parameter L, which goes from 0 to 4 all the way through 11. So it's modulo 12, but it follows this arrangement here. Now for the different values of L, we actually place the 4 variable pilots, and notice that the pilots are at equal distances with each other. So we place the 4 variable pilots for the case L equals 0. For L equals 2, again we change the pilot locations for the next symbol. For L equals 4, which is for the third symbol, again the pilot locations change. And then after the 12th symbol, we go back to L equals 0 and we repeat the whole process again. So as you'll notice, the pilot locations for the 12th OFDM symbol is the same as the case shown over here. So in the uplink subframe, for each data burst, each subscriber has to allocate both a fixed pilot and a variable location pilot, and the location of the variable pilot changes on a per symbol basis according to arrangements shown over here, and the details are in the standard. Again, the benefit is the fact that each subscriber station has its own set of pilots, and we get diversity by changing the locations of the pilots, especially important in the case of fast fading channels, as can be expected. And also in a fixed wireless network, this is very important because, again, we achieve diversity, where if we had a deep fade, for example, all the pilots would not be eliminated. If they were fixed in that deep fade location because of the fact that they're variable, then we have diversity effect. So we have a diversity gain in this sense, even for fixed wireless networks and also for mobile wireless networks.